So I'm going to introduce him in Spanish. So, Gabriel hizo sus estudios de licenciatura, maestría y doctorado en la Universidad de Sherbrooke, en Canadá. Y estuvo trabajando durante el doctorado con dos investigadores excelentes, que es Maxime Decoutot y Rashid Dirich. Personas muy bien conocidas en nuestra área por su alta calidad en cuestiones de procesamiento de imágenes. Por supuesto, está plasmado en el trabajo de Gabriel. Gabriel es muy amable, lo invitamos estando en Suiza y decidió que podía venir y estamos muy agradecidos de que haya aceptado. Nos va a dar una presentación fantástica acerca de tractografía informada con microestructura. Entonces, nada más como introducción del amplio CV de Gabriel, si ustedes buscan en sus publicaciones, en sus papers, van a ver que hay varios factores. Uno es reproducibilidad, en el sentido de que Gabriel ha estado involucrado en desarrollo de software, en particular DyPipe o Tractometer, que es software para validación de tractografía. Entonces, en sus publicaciones van a ver siempre los keywords de reproducibilidad y quantitative. Entonces, me parece que es una persona que está muy interesada en proveer nuevos métodos, sobre todo computacionales, que nos permitan obtener medidas cuantitativas útiles. Entonces, él está muy metido en ese tipo de áreas y en particular nos va a platicar en esta sesión sobre Microstructure Informed Tractography, que va en la misma dirección. Tienes unos datos, pero cómo puedes obtener información que valide y que te dé, que mantengas la información que realmente indica las propiedades del cerebro y cómo puedes deshacerte de información falsa. Creo que es algo de lo que nos va a platicar. Okay, so thank you very much, Gabriel, to be here. And
thank you very much for the introduction. Thank you for the invitation to this meeting. So my talk will be on white matter tractography, and I will focus on microstructure informed tractography and the recent development to improve the white matter reconstruction using additional information than the fiber orientation only. So as you might know, tractography, supposed to be a video. Tractography is the process that take diffusion images and use this information to reconstruct a 3D model of the white matter. And in this talk, I want to show some techniques that use information from anatomical image, from a T1 image, especially on the type of tissue, white matter, gray matter, CSF, and on the shape of the brain. Also, I want to show some techniques that use microstructural features that are extracted from diffusion MRI to overall improve the reconstruction of the brain using tractography. So why tractography is important? One great application field where it has success is in neurosurgical intervention planning. So it's very useful to know where are the white matter structure for the neurosurgeon to decide which tissue to keep, which tissue to remove, how to access the tumor, on which side of the brain it should enter to remove the tumor, and overall how the tumor change the functional network of the brain. So tractography might be very useful for this kind of application. Also, a very useful application now is to study the brain structure and function and the link between the structure and the function. And also to study how white matter change in case of neurodegenerative disease, for instance, demyelinization of the axon, and if tractography might be useful to predict and see how these properties change in the brain. So let me start with a small introduction on diffusion MRI and white matter tractography. So as you might know, diffusion MRI is sensitive to the motion of the water molecule in the brain. In the case of water, like in this jar, the water molecule moves uniformly in all orientation, following the Brownian motion. But in the brain, the water is restricted in the direction, especially in the direction perpendicular to the fascicle, to the axons, and is less restricted in the direction parallel to the fascicle. So diffusion MRI is sensitive to this phenomena. It's also sensitive to the packaging of the axon and the size of the axon. So depending on the way we acquire the image, we might be able to recover this kind of property from diffusion MRI. One of the most common way to extract the orientation from diffusion MRI is through spherical deconvolution, and the hypothesis is that the true fiber orientation in the brain is modeled as a convolution as the typical response function for one fiber population, given the diffusion sequences. And this is the signal that we acquire. So if we invert this problem and estimate the response function, for instance, from the data, or if we have prior information on this, we can deconvolve the signal and get an approximation of the true fiber distribution in the voxel. So this is the goal. This is the state of the art to extract the orientation in the brain and do tractography. And with this, we can extract the fiber crossing in the brain up to about 40, 45 degrees. Let's move on to tractography. So this is a coronal slice of a brain. In each voxel, I plot the orientation, the main orientation of the structure. So if we zoom in, we see the fiber orientation with the crossings, and we have this for all voxels of the brain. So tractography uses this information. So for instance, if we start the seeds in the middle of the corpus callosum, we can follow this orientation until we reach the gray matter, and we get a set of fiber that represent this fascicle. So there's two main family of tractography algorithm. The first one is we call deterministic tractography, which we do discrete step size and follow the main direction of the fiber ODF. So this is the maxima of the fiber ODF profile, if you will. So iteratively, we follow the main direction until we reach a stopping criteria, for instance, the gray matter. And we have the probabilistic tractography, which is more able to explore more direction as it follows the direction weighted by the value of the fiber ODF. So in this case, most likely we will follow the main direction of the FOD, but we can explore more directions. So if we do that all over the brain, putting seeds in every voxel of the white matter, we can get this kind of reconstruction. And then we can use our knowledge of the anatomy to extract the main structure of the brain, main fascicle that we know that exists in the brain. We can use automatic tool to try to extract those fascicles. So those fascicles with what we call the valid connection, the true connection that are in the brain that we know exist, and we can obtain well with tractography. But if we look more closely in the set of streamlines that tractography produces, we see a lot of those small connections that are anatomically invalid as they start maybe in the gray matter but stop in the CSF or stop in the white matter. We call those connections the no connection, and depending on the parameters and the data, it's somewhere between 15 and 50% of the streamline that are reconstructed that are no connection as they connect nothing in the brain. And most likely they are either part of valid bundles or just error in the tractography. We also have what we call the invalid connection, or sometimes the false positive, which are streamlines that connect region of the gray matter. They might be good, they look good, but most likely they are not, as we have at least we don't have evidence that they exist in the brain. And those streamlines are very problematic, as they will appear in the analysis of the data for neurosurgical planning, for instance. They will appear in the connectivity metrics when we look at the structural connectivity profile in the brain. And we don't know how many of these streamlines are in the brain. So these are very problematic when we look at the whole set of streamlines from tractography. So why do tractography produce those no connection and invalid connection? Why not only valid connection? There's many factors, essentially noise, error in the reconstruction, limit of the diffusion data, resolution, acquisition scheme, and also all the tractography parameters that we use, the volume in which we want to reconstruct the streamline, where we place the seeds, how we select the propagation direction. All those factors might produce, in the end, no connection or invalid connection. So I want to start with techniques that help improving the tractography algorithm by injecting anatomical priors in the tractography. And then I will move to microstructure and from tractography, which use really the size of the axon to improve the overall reconstruction. So let me start with anatomical information, and especially the partial volume fraction estimation from the brain and the brain shape. So this is a T1 image. We can use tools, software like FSL Fast that will segment this image in 3 classes: white matter, gray matter, CSF. In each voxel, we have the sum of the 3 compartment equal to 1. So this is quite easy to obtain, and this can be very useful, as you will see, for tractography. The typical way to use that is to take a binary mask of the white matter and set that for tractography, this is the volume in which we want to reconstruct the fibers. But if you look closely at this image, you see that there's some hole in the brainstem. So tractography that goes from the cortex to the brainstem will stop in this region because they're just, actually the mask says to tractography to stop there. And we also see very narrow white matter pathways near the cortex. And if you look at the partial volume fraction map, you see that, in fact, these voxels contain not 100% of white matter, but both gray matter and white matter, similarly in the cortex here. So actually, the mask is much bigger than the binary mask that we sometimes select for tractography. That might be very useful to use this information at the time of the reconstruction. And so if we use this information, we can determine where the tractography should continue. It's in the white matter, where it should stop when it reaches the gray matter, and where it shouldn't stop and wrongly stop in the CSF. So this, with the partial volume fraction map, we can do that. And actually, two techniques use those maps, which are called anatomically constrained tractography, which is available in a matrix, and also continuous map criterion, which essentially threshold and interpolate those maps while the tractography is going. And ACT put a threshold to define whether it's white matter, gray matter, or CSF. And CMC use probability that are derived from the partial volume fraction to define the state of tractography. So if we have those maps, and we know from those maps and those techniques in which kind of tissue we are actually tracking, we can detect that we reach the CSF, for instance, and it's a wrong position for tractography. We know that the streamline or the axon shouldn't go there. So when we detect that, we can move back with the technique that's called, actually I didn't introduce that, but it's called particle filtering tractography, which the technique tried to recover a valid segment when we find a wrong segment in tractography. So the first thing, we detect tractography reach the CSF or stop in the white matter. Then we backtrack a few tracking steps. And then we start multiple tractography, multiple streamline locally. And we weight each of the samples based on the anatomy underneath. So if it goes in the CSF, we penalize the streamline. If it stays in the white matter, we increase the weight. And we do that until we reach a stopping distance, a maximum distance. And then we draw from the final distribution a valid segment. And this way, we recover the streamline that was previously lost. And then we restart the tractography normally. So if I show you the same thing but animated, we track. We reach a stopping criteria that is invalid. We backtrack a few tracking steps. And then we start tracking in parallel, if you will, and weight the samples based on the anatomy. So the white here is the CSF. The black is the white matter. We draw from the final distribution, and then we continue the tracking normally. So this way, we kind of bounce on the wall of the CSF instead of stopping wrongly in the tissue. I would just want to show you this quickly. If we put a seed here in this very hard and complex geometry, so the goal is to reach the two green points. We see that in the highly curving region, the streamline reach the wall and then have to fall back, find a valid segment, and then continue. And for some area, you don't need this technique. You can just follow the main direction, for instance, and then again, you bounce on the wall, and you use the knowledge that the axon shouldn't go in the CSF as prior information to find an alternative valid pathway. And once you're done, you have a streamline that will be otherwise very difficult to recover. So, and especially in the brain, in some area where the white matter fascicles are close to the CSF, it might be very difficult to reconstruct. And with this technique, we can recover more of these streamlines that are near CSF and difficult tracking regions. So just before I move on, I just want to show you the evaluation that we made, the tool that we developed, which is what you mentioned in the introduction. It's called the tractometer. So with this tool, we essentially know the ground truth connection, endpoints to endpoints, and the volume of the fascicle. So it's a simple toy example with tube, with different radius, different length, and different curvature. And we can generate the diffusion signal at different SNR and different sampling scheme. So we can test tractography using different data sets. And we know the ground truth, so we can compute the valid connection, the streamline that connect the expected region, the invalid connection, streamline connecting region that shouldn't be connected in the model, and the no connection, again, the streamline that stops in the middle. And from that, we can report for one tractography algorithm a score in terms of those three metrics. And we can also look at what we call the valid connection to connection ratio, which is essentially the fraction of valid connection over the total number of connection. The thing is that those connections, those streamline, we can remove them from the tractography result before doing the analysis because they don't connect the gray matter. We can detect those streamline, but we cannot detect those. So this ratio is kind of interesting in terms of precision of the algorithm and accuracy in the reconstruction. So now if you want to run the probabilistic tracking algorithm with and without Ph.D., we see that this phantom is very difficult to reconstruct as it has way more CSF than a typical brain. So their CSF are everywhere around the tube, essentially. So it's normal that the number of no connection is quite high, around 60%. If you use Ph.D. with the technique I just presented, we can drop that to about 10%, which is interesting. So now 9 seed that we put in the volume out of 10 will result in a streamline connecting two regions. And the ratio of valid connection over the total number of connection will be very similar previously because we essentially address the problem of no connection and as a whole the distribution of the streamline in the brain. So good experiment on simulation data. If we look in the brain with a deterministic tracking algorithm, but with this Ph.D. techniques, when we detect invalid stop, we see that we can drop from about 30% of no connection to 5, and with the probabilistic tracking of about 15% to 4. And we can get nice fascicles that we want to segment in the brain. Especially, we do that using just the information from the partial volume fraction instead of a binary mask, essentially. So then we wanted to apply these techniques on say, real application in the brain to identify fascicles. So here's the part of the brain. The frontal part is here. We have the eucinate fasciculus, which is in the hook here. And the inferior frontal occipital fasciculus, we connect the front to the back. So if we look closely in the anatomy with dissection, we can see first on the outer layer kind of set of axons that connect the side of the temporal lobe and the frontal lobe. If we go a bit deeper, we have this long streamline connecting the more superior part of the frontal lobe and the side of the temporal lobe. And then if we go even deeper, we can see 3 other sets of fibers with different length. So we can see that with a dissection of a brain. So can we see that with tractography? So what we try is to run this probabilistic tracking algorithm with the particle filtering tractography on the whole brain. Then we segment all the streamline going through a small region where all those axons were going through in the brain. So we get this subset of streamline. And we did that for 30 LT subjects. And for each subject, we segmented the fascicle associated to it, and we look at what we can get in terms of white matter reconstruction with tractography. And we see a lot of similarities between all the subject and all the left and the right side, but we note one big difference between the left and the right. So this was very useful to use the partial volume fraction maps to better recover the full length of the connection of the eucinate fasciculus. So another very important thing, other than the mask, is the way we place the seeds to start the tractography. So if I give you those 3 fascicles, so one short, one twice the length, and one 4 times the length of the short, and we place seeds in all voxels of the volume, we get this kind of density map. So this is the color is related to the number of streamline crossing the voxel. We can barely see the short fascicle with high intensity for the long one. So essentially, if we look at in terms of number of fiber and density of fiber, this fascicle looks much more connected somehow to the shorter one. So this is a problem. It means that in the brain, the big structure in the brain will be overrepresented if we put seed everywhere in the brain compared to short bundle. So if we put instead the seed in the green part at the interface of the bundle between the white matter and the gray matter, we can get a much more uniform reconstruction in terms of density and number of streamlines. But then in the brain, how we define the interface is not easy. Which voxels are part of this interface? And overall, if we do that in one way or the other, using, for instance, the surface from FreeSurfer, or if we look at, for instance, here it's the voxel that contain both white matter and gray matter. It's a way to identify the interface. This will reduce the length bias. But as I said, those voxels is very hard to identify, and also the diffusion direction that we have in those voxels are not ideal because we have gray matter and white matter, and the model that we use for extracting the diffusion direction might be not optimal in this case. So how we can go, how to go further than that? Actually, there's another problem I want to mention. It's called the Girard bias problem, where if we look at tracer study, in a gyrus, we see that the accent tend to start on all the side, on the wall of the gyrus, goes in the middle, and then converge and go connecting some other region, other structure. But if we look at tractography, most of the streamline ends up in the upper part of the gyrus, essentially because the resolution is so poor that we don't have enough voxel to capture the complexity in the region. So in the end, we get something like that. So it's very hard to address the profile of connectivity or where the walls of the gyrus are connected. So the gyrus become one region instead of a surface where we can try to find connectivity profile in the brain. So one way to kind of solve the interface problem and try to reduce the bias, the Girard bias, is to use a technique that is called surface enhanced tractography, which inside use a surface flow technique. So here we have a mesh of the interface, for instance, from FreeSurfer. Then we have a few parameters, a diffusion weight, which essentially weight the speed at which the speed of the flow somehow. We need the mean curvature of every vertex on the mesh and the normals to the mesh. And then we can run this process over and over again, and this will smooth the mesh in the direction of the normal and where the curvature is stronger first. So somehow the brain will become smooth and shrink following the curvature of the brain. And if we do that and follow each vertex, how they move following this flow, we can get some segments from the original surface, which is green, to the red surface at the end of the flow. So this way, we can start tractography not positioning a point in the voxel, but we have a segment, we have an orientation, and we also start in the white matter at this place. So in this way, we can seed from all the vertex, all the small segment, everywhere from the walls, and get inside and follow the white matter structure, and do the same at the end of tractography, instead of ending in the end of the gyrus. So overall, doing that, it's increased the surface coverage and also increased the reproducibility and the specificity of the connectivity matrix. So the distance intra-subject and the similarity between the matrix for multiple acquisition of the same brain. So good. We reduce some biases and we help the seeding of tractography. So just to conclude with the anatomical prior, from the high resolution T1 image, we define the mask, from which we can define where the streamline connect the gray matter and where they shouldn't stop in the white matter of the CSF. And overall, we can get streamline that more uniformly cover the Girard surface or the walls of the gyrus. Overall, we reduce the bias in length, in shape, using the particle filter, the size and the position of the fascicles if they are near small CSF region. And we also reduce the bias with the Girard surface. However, the dangerous part of that is that if we have errors in the partial volume estimation maps, this will affect the reconstruction. So if we have error in the volume or the segmentation of the image. Also, the registration between the T1 and the DWI images is very important. And it's also very challenging to do if they are tumor or if it's an unhealthy brain, the parcellation of the brain might need more classes, and then you need more attention to obtain those maps correctly and to define the behavior of tractography using those maps. So it might be very useful, but there's some danger that we have to pay attention. So let's say that now we have ideal tractography mask, ideal seeding techniques, and that the fiber orientation is very good. Will we have still error in the tractography? Well, the tractography will be perfect if we have ideal mask and local reconstruction. And the answer is no. It's no, because if I give you this set of direction and I ask you what is the underlying structure there, you couldn't tell me. There's two options, there's two configurations that will result in the same volume, the same local orientation, and actually there's ambiguity in the direction. So you can be either of those two configurations, it's called a crossing configuration or a kissing configuration, but because the two bundles are perfectly parallel in the center, there's no way to distinguish solely based on the orientation which of the two structures are there. Even if everything will be perfect, no noise, infinite resolution, we won't be able to distinguish any of the two. Actually, tractography will most likely give you the four possible configuration and let you deal with based on prior information that we have when you segment the streamline, but you will most likely get the four bundles. And last year, there was a challenge at ISMRM with simulated data that looked like a brain. So they took 25 streamline bundles from high-resolution IGP dataset, and then they simulate the signal giving the orientation of the lines and the position in the brain. So we get a brain that that is simulated, that look like a brain in the terms of size and shape of the bundles. But in this case, we know where the streamline should stop and where they shouldn't go. So 20 teams submit 96 reconstruction. And if we look at how they did in terms of valid bundles and invalid bundles, we see that most of the team managed to find the 25 bundles. But however, they find also 88 invalid bundles, which is a bit scary as those bundles will affect the connectivity matrix. And overall, about 50% of the connection were good. So still, this problem of, even with the noiseless data, when we run tractography on the ground truth images, without distortion, without noise, we still have a lot of invalid bundle and invalid connection due to the ambiguity in this direction. So if we zoom in the simulation data and we look at how many bundle cross in this very specific region, we see that up to 5 bundle cross in the same voxel. So ideally, we will need 5 peaks representing the orientation of every fascicle. If we look at the signal peaks, the ground truth signal peaks, so without noise, we see up to 3 peaks. So we miss some peaks there. And if we look in the same region in the data set, the HEP data set that was used to generate the data, we see that we only have 1 or 2 peaks, even if there are 5 bundles that were segmented there. So that's a problem. So how we try to solve this issue is to inject in microstructural information in the reconstruction. And there's 2 families of techniques that do that. The first one is called the bottom-up approach, which essentially rely on local modeling of the diffusion signal. So the idea here is to inject information at the time of the reconstruction of the streamline to reduce the false positive using additional information. And also, in the end, we can extract microstructural feature out of this. The other family of technique, which we call the top-down approach, filters the false positive from a pre-computed set of streamline. So the idea here is to associate a diffusion model to the streamline and try to see which streamline contribute the more to the signal and penalize the streamline that don't help explaining the data. And in the end, removing those streamline and hopefully getting a set of streamline that has more valid connection than invalid connection. We can also get the microstructural feature. So let me start with the first approach. So the technique is called extract, and it's a deterministic tractography algorithm as I showed earlier. So it follows only the peaks of the fiber ODF, but is guided by the axon diameter index, and I will tell you what this is. So to do that, we need in every voxel the peaks of the fiber ODF, and we need a model to get the axon diameter index. This model is called the ActiveAx model, which I will show you right now. So essentially, how we model the signal is that the diffusion signal is modeled as a weighted sum of kernels with different weights. So we will be looking for the weights and some noise. So this dictionary of kernels for the ActiveAx model is composed of isotropic diffusion profile, so diffusivity equal in every direction. We model the intra-axonal part as a set of cylinders with different diameters, and the extracellular part as a Gaussian with more diffusivity in the parallel direction, and the diffusivity in the perpendicular direction are fixed. So essentially they are Zeppelin or the cigar-shaped tensors. And we have this set of compartments for every direction of the fiber ODF. So this is the model that we want to fit. So if we run the optimization and get the best weight, given the dictionary of kernels, we can extract the coefficient associated to every cylinders, and then we can compute the mean cylinders in every direction. And this is what we call the axon diameter index. So we have one of these for every direction of the fiber ODF. So a typical tractography algorithm here in orange will follow discrete step, reach a position where we have multiple peaks. So we have a choice to do which direction to pick. Conventional deterministic tractography algorithm will pick the direction typically that minimize the curvature. So it's one way to actually there's no information to help you pick one of the two. So we have the hypothesis that the axons are relatively smooth in the brain, so we pick the direction that reduce the curvature essentially. With extract, we have more information. We have the axon diameter index for each direction and also for each previous direction of the tractography. So now we can approximate we can compute the axon diameter index of the current streamline that we are tracing, and then pick the one that better match what we are actually reconstructing. So essentially we use the information from the previous steps to pick the direction of the next steps. So if we compare the two algorithms on this simulated data set, so it's a kissing to fiber bundle crossing by kissing in the middle, we get those two valid bundle. As I said earlier, we get it very easily with tractography. We also get those two, which is about, in this case, 40% of the streamline are wrong, and are those actually the crossing one, which are not the true one in the data. And this is kind of easy to imagine how tractography behave. If we look at only the direction, we see that once the tractography reaches the middle part, there's no way to find out which direction to pick afterward. So it results in essentially 50% chance that it's the good or the bad direction. But now with extract, we still get, actually the thing I didn't tell you is in the data, this fascicle is 2.4. The average diameter of the cylinder, of the axon if you will, it's 2.4 micrometer. And for this one, it's 6.9. So the deterministic tractography algorithm didn't pick the difference, but with extract we can. So again, we get those two. But now the false positive is about 10% instead of 40. And this, again, it's kind of easy to imagine how the tractography behave, as if we start the tractography in the peaks, here the size of the peaks is proportional to the axon diameter index. We follow big peaks until we reach the middle, which is about the average. And then when we reach the crossing, we know that from the previous step, we should follow the big peaks again. So again, here in the crossing, it becomes very easy to identify which direction to follow. So we have much more information now to identify which direction to follow with the tracking algorithm. So if you run that in the brain, we get those kind of maps. So there is no smoothing, it's just the value on the points of the streamline. So we see that locally it's kind of spatially coherent. And if we look at the median value along the streamline, we see, for instance, higher value in the streamline starting from the motor area going down in the brainstem, which is what we will expect from the anatomy. If we look some fascicles in the brain, if we look at the overall distribution of the value along every point of the streamline, it's relatively flat distribution. But if we look at the median along the streamline, we see differences across fascicle. And also the change in the value in the direction is also expected somehow if the fascicle cross in the same, become parallels in the same voxel, as in the middle of the kissing phantom. So okay, we can pick differences across fascicles. Yes?
Regarding your coloring of the median, so that is the median of the entire streamline? So the entire streamline has one single color?
Yeah, the one streamline has one color, which is the median of the axon diameter index. So one value per streamline in the histogram, essentially.
And this is per segment?
This is per point, per segment of the streamline. So now we were curious also to see what was the effect in terms of density of streamline for the subset of fascicle that we identify. And what we did is to fix every parameters of tractography, the mask, the seeding, the fiber ODF estimation, everything was the same except the way we pick the direction for tractography. And if we do that, we see that overall there's an increase in the fiber density for those subset of fascicle. So there's many possibility that could lead to this increase without overall increasing the number of valid connection in the brain, but at least it's a good sign to see that the density increase. So for those subset of fascicle, the number of valid connection increase, and potentially the invalid connection or the no connection decreases. So it was just an observation. And if we look at the value for 34 subject on this is the mean of the axon diameter index along all the points, we see that for different fascicle, we have different value essentially. The variability is quite high, but at least we can pick some differences and some similarity from left to right. And if we compare to the FA, the mean FA along the fascicle, we also get this similar range of value, but the trend is very different. So hopefully it can be a different kind of metric that we can get along the fascicle to study. And last figure for extract, if we look at where the direction was changed from conventional tractography algorithm, we see that this appears in the white matter, in the dense white matter, where there's multiple crossing and the crossing angle is low. For instance, in this region, we will expect to have kind of a 90-degree crossing between the corticospinal tract and the CST. But actually, in this case, we don't need the axon diameter index because the angle is already too big. But in this area, the angle is lower. It's maybe around 40, 50 degree. In this case, the axon diameter index can help. And overall, when we have multiple choice, the axon diameter index help or change the direction in 19% of the time. So essentially, the deterministic tractography algorithm is good in the majority of the cases. So with that, we help reducing the invalid connection at the time of the reconstruction. Now let's move to another technique, which filter the streamline after the reconstruction is done. So I will discuss about the COMIT framework, which is convex optimization modeling for microstructure and from tractography. And put it simply, the goal is to approximate the diffusion signal given a tractogram, a set of streamline, and a model. So in this case, we model the fiber as a stick, so just this kind of response function. And then we try to approximate our diffusion signal giving this dictionary. So essentially the green voxel, we are looking for the weights, and the green voxel could be well approximated by fiber 1 and fiber 2, and the rest should be 0. For the blue voxel, we only need fiber 1, and for the yellow voxel, we need only this coefficient. So if you run the optimization for that, we can find that fiber 3 is not useful to explain the data. So in this case, it was binary value, but you can imagine here a weight. So each streamline contributes to a level to explaining the signal. And then we could put any kind of model here with more complex, for instance, the one that I used earlier with extract with the cylinder and the Zeppelin and the balls. So we put a lot of coefficient. Actually, it's what we did. Then this is the same model that we use for extract with the cylinder, the Zeppelin, and the balls. So now each fiber has multiple potential contribution to the signal with the signal that we know from this kind of configuration. So if we run this on, this was ex vivo macaque data on the corpus callosum, so on those fibers, and we run the optimization, we can pick something that it's quite interesting, where we have lower value in the frontal part of the corpus callosum with higher value in the middle, and again, average or lower value in the posterior part, and which seems to be what we see with the histology. Higher axon diameter in the body of the corpus callosum, medium at the end, and small in the frontal part. So this is interesting that we can pick this from this data set. We then done that on in vivo data from the adult diffusion data set. Again, we seem to be able to pick higher diameter. So this is actually the different diameter and the contribution of each streamline for the distribution of diameter. So we see that a lot of the value are for very low diameter, which essentially everything below 2 micrometer look more or less the same in diffusion MRI with this sequence. So a lot of a big part of the signal goes there, but then we have this distribution that seems to be bigger in the body of the corpus callosum again. If we look now with another data set with multiple diffusion time, so we hope with that we are more sensitive to the diameter than with the previous data set. If we run commit and get the diameter for all the streamline in the brain, and then we segment the different bundles, and we look at the mean diameter, this is what we get. So the first part is the corpus callosum, the 5 region of the corpus callosum, and then we have the pairs of other bundles. And especially in this case, we see that the value that we get is very similar to what we would expect with higher value in the body and medium value at the end. So this is quite interesting work. This is still work in development. The publication is maybe coming soon, but we are really playing with high quality data from the connectome scanner to try to be able to be more sensitive to smaller axon and more sensitive to bigger axon in the end. And if we also, by running commit, we can get the fraction of the signal that is explained by compartments that are, for instance, in the case of active-ax cylinders, so intracellular compartment, extracellular compartment, and isotropic compartment. So if we want that, we can get those maps, which are quite interesting as such. And hopefully, the streamline that are not contributing to those maps are the one that we can left out of the tractogram for further analysis. And just to give you a small tease on what we can do, again, I come back with this phantom, where we know the ground truth in terms of the signal and the density of the fibers. So if we run the probabilistic tractography algorithm, the simplest one, we can get the 27 valid bundle, but in the end, we get 235 invalid bundles and about 60% of valid connection. If we run commit and filter the streamline that are wrong up to a fixed threshold, in this case, it was arbitrarily chose, but we still can keep 27 valid bundle and reduce the invalid bundle to 18, which is quite impressive, and we increase the valid connection from 60 to 80%. So again, this is work in progress, but it's quite intuitive also that we can use the signal to filter the streamline a posteriori. So to conclude on MIT, we use the signal from the high resolution, densely sampled diffusion MRI images to estimate the microstructure. And with that, we can distinguish different fascicles. And we can hopefully reduce the fraction of false positive. We can estimate the microstructural feature along those fascicles, but we need to set a model, which can be problematic, as it's quite simple model in the end when we look at the complexity of the actual structure in the brain. On AXTRAC, it's very challenging to estimate the axon diameter index when there's more than 2 or 3 directions, so we are quite limited. And also, the tractography can only follow the direction of the FOD, so we cannot explore as a probabilistic algorithm, for instance. With Commit, if we want to do the fitting of the data with the streamline properly, we need all the true positive. So with this, if we have all the true positive, we can filter out the false positive. If we miss a fraction of the true positive, Commit will fit invalid connection to explain the signal where the missing true positive are not there. So ideally, we will need all the true positive plus maybe many invalid connection, and then we can obtain all the true positive in the end. And overall, where I think those techniques are going in the future is to do both the estimation locally using the microstructure and using kind of filtering approach, or if you will, with global tractography algorithm where we reconstruct the whole brain, explaining the signal and getting the connectivity at the same time. Like the technique, the spin glass technique, if you know, for instance, where we try to place segment and connect segment in the brain, and then we can, for instance, do that using the microstructural information. So this concludes my presentation. I thank you very much for your attention, and I'm ready for questions if you have some.
Okay, thank you very much. Very, very nice presentation, very interesting. So let's switch to the question time. Preguntas en general pueden ser en inglés, en español.
How do you select the partial volume estimation map?
You have to rely on a software, actually. I'm not expert in the way you do that, but essentially the technique that we have today rely on the intensity of the image and the spatial position of the voxel. There are several techniques to do that. For instance, if you look at the paper of FSL FAST, you could also register your images in an atlas where you know a priori maybe with good manual analysis, you know where what is the fraction of CSF, white matter and gray matter, and then you can apply it to your brain that you're actually interested in. But you need a way to estimate it. I mean, there's no.
It's an open topic to work.
Yeah, but there are many techniques to do that, but it's hard to validate. So I guess we have to stick with what we have for now. But I mean, as the technique will improve, the tractography that use it will improve as well. So if you have error in your reconstruction, you inject that in the tractography somewhere. Yeah, as the technique will get better, it will be better as well for this technique.
Okay, thank you.
Good.
Thank you for the talk. It was really great. It's a cool set of tools that you have, and I was specifically pleased that you suggested that the tracking should start not really at the interface of the gray and white matter, but that you rather move a little bit down into the white matter. Is there any biological interpretation of the surface flow that you use to smooth the surface? Or is it depending really on the curvature, how much you smooth the surface at the end so that you are further in the white matter in a gyrus and not so much down in the white matter in a sulcus? Is there any potential problem with that you are like very far in the superficial white matter when you are in a gyrus, but very close still to the interface when you're at a sulcus?
Yeah, I think the tool I showed is, again, those things are not even published yet. It's very, I think it's coming very soon, but it's very first iteration of this. So of course, what happened at the bottom of the gyrus and at the top of the gyrus will be very different. But I think we can think as the way the brain develop and the complexity of the surface evolve. So somehow we try to reverse this process and get into the gyrus. But it's an approximation, a way to get from the interface that we get from free surfer, for instance, toward the white matter. But yeah, you have to put some constraint on for instance, you go only in the direction inside, so you don't have kind of the bottom that goes up in the CSF, for instance, in between the gyrus. So it's an approximation, it's a geometrical approximation, but it uses the shape to kind of get into the interface.
A competing model that Louis may also know is that you could also fit a Laplacian deformation field from interface to ventricles, and then just follow this. So you peel the white matter like an onion in a way, and this way you also
somehow it's what it is doing. I think
Okay,
you can probably make the link between the two. I'm not the one behind the development of this tool, but I think it goes toward that. If you continue the process until the end, you will reach the ventricle. Essentially, you will have a ball in the middle. So you have to fix somewhere to stop,
Yeah.
which can be an issue also. But yeah.
Yeah, no, but I think it's really good because I mean, do you have quantitative estimates of how much the false positives drop by
With this technique, no, because we can only do it more or less. I mean, we will need a simulated data set that have the T1 as well and the shape. And but if we look what we did to try to validate, and I mean, this makes sense as a way to see it. I mean, it makes more sense than just placing randomly or just on a ribbon the seeds. But what we did is to look at the connectivity matrix. So again, there's many ways to compute that matrix, but we select some standard way to do it, and we look at the differences between multiple scans of your brain, for instance. And the distance between multiple acquisition of your brain was smaller using this technique, which is good, so it's improved the reproducibility somehow, and the distance between subject was increased. So this is a good sign that something meaningful is extracted from this shape for the seeding. But
Gracias. That was a very nice talk. Thank you very much. It's a very clever idea to use the incoming microstructural information to propagate the streamlining areas of kissing and crossing. But I have a little bit of trouble understanding what is really going on in the kissing or overlapping section, or how far or how short should it be such that the information that is coming is still retained so that you know where to exit. Because at some point during the overlap, I can see how you could have a bimodal distribution of axonal diameter, but I don't understand how you could have the idea that there are two peaks. I mean, you could have the same, just one single bundle that has a bimodal distribution of axonal diameter, but it's just a single fiber, as opposed to understanding that now there are two fiber populations that are mixed here.
yeah, actually, first of all, if the two fiber population have the same microstructural property, there's no way to distinguish them using this technique. So they need to be different. And the way that the technique works is by seeding, starting the tractography where the two fiber population are not together. And then you need to find a way to, how important is the previous step to pick the direction afterward? Because as you said, when you reach the middle, if it's too long, it will kind of change your estimation of the fascicle. And then when you will exit the kissing, then you will be confused. So there's a parameters that we use in the tracking, which is essentially a kind of sliding windows where we take the median. We take the median especially for that, because the mean will be drift toward the mean of the two population, but the median hopefully, so essentially we have to balance the size of the window and the potential overlaps, the length of the potential overlap between the fascicle. But it's not trivial. I mean, the good thing is that in the worst case, say that the estimation is wrong and the overlap is too long, the result is not worse than typical tractography algorithm. I mean, if somehow you will just pick randomly, which is fine. You still have this cone that limit the maximum curvature. But if you happen to have enough information to select the direction, there's a benefit, I think, there. But again, it's very hard to also validate. But at least on simulation, it worked extremely well.
That's very clever. And I'm sorry, one more question, quick one. Is there a danger when you're doing your backtracking algorithm that essentially forces its way bouncing through the walls, is there a danger of overfitting and just relying on just the morphology of your white matter mask?
Yeah, it could introduce some type of false positive, where, for instance, especially I think if the segmentation is wrong in some area, and we see that if we apply these techniques, we get a couple of streamlines in the brain that, for instance, go up in the gyrus, somehow manage to bounce and then come back, which is what I showed with the kind of the very curvy bundle. So somehow this can happen. So, or if you bounce on the ventricle, maybe use a probabilistic algorithm, somehow you will find a way that is very unlikely, but manage to stick in the white matter, and it's the only way, and maybe the problem was earlier, or so yes, it can introduce some kind of new type of error, if you will. But overall, I think the benefit is there.
Okay, great talk. Thanks very much.
Thank you.
We have many questions.
Thank you. I echo great talk. I have just two questions. The one is really when you come in from the gray-white surface and you seed just inside it, how are you overcoming the distance bias in probabilistic tractography?
What do you mean?
If you brute force seed, you overcompensate for the distance bias that's in probabilistic tractography. The sort of brute force cylinder model that you had, I was curious what you were representing in terms of the FA, the tensors that you were using, because if you have crossing fibers throughout that cylinder, you will not have that overrepresentation, because as you take each step, you're less likely to reach the other end. So you have a distance bias problem if you seed from the surface, but you have overcompensated for it if you seed from everything.
Yeah.
I wonder what you...
But if the fascicle is longer, you have more chance to introduce error along the reconstruction. So if the longer the fascicle is, the harder it is to track. With the cylinder, we fit the cylinder in each direction of the FOD. So the problem of the fitting there might appear if we have, for instance, two fiber at 20 or 30 degree, which look like a single peak. So the estimation there might be wrong because you have kind of a dispersion effect on the direction of the fiber. So this can could introduce error in the reconstruction. But then for the gyrus wall, by putting the seeds everywhere, you might overrepresent some part of the wall, depending on the way the mesh was structured. But essentially, you start a tractography from one of the segments, and if you fail to reconstruct the streamline, for instance, if you start in an area where you only have a few voxels of white matter and then it's surrounded by gray matter or CSF, you remove those streamline in the end.
Yeah.
So
no, I suspect that you will have an overrepresentation of short distance connections and an underrepresentation of long distance connections. Whereas if you brute force, you probably have the opposite of that. But
yeah, true. Maybe you will have also a lot of connection connecting the one side of the wall to the other side.
yeah.
And actually, where you stop the surface flow will affect if you stop too early, the two segments on both sides will kind of pointing toward each other. So depending on the shape of the FOD and your step size and your parameters, you might not be able to go down and you will connect wall to wall. If you smooth or if you let run the flow longer, those lines will go toward the main direction in the middle of the gyrus, so you might be able to go far away then. But yeah, it might be true that the short, somehow when you do that, you represent the density of the fiber that you get for one fascicle is kind of proportional to the interface in which it goes and project to.
Okay, so question two. I love the idea of using the microstructure, the information to feed back on tractography. What do you gain if I give you not only T1, but I give you naughty, I give you MT sat?
Yeah, actually, this is where I think it's going. The diameter is one thing, but there's other thing that the important thing is that we need something that is bundle specific, or at least bundle specific locally. So if we need something that is direction. We can, for instance, if you look at the dispersion parameters in every voxel, it's not specific to one of the peaks somehow. It's a low. You estimate it voxel-wise. So you need some parameters that are direction-based. And it needs to be something that is related to the fascicle that you want to, not necessarily for the full length of the fascicle, but at least locally you expect from voxel to voxel that this value will be somehow consistent. If you have that, you can kind of use the information very locally to pick locally the direction that you want to follow afterward. So the diameter is not the only thing that you can use, but there's not, as it is today, there's no many things that you can estimate that is direction specific and fascicle specific.
Hi. For this algorithm, how many B values and directions do you need, or do you use for that?
You need the type of diffusion images that you can get on the connectome scanner, essentially, or ex vivo animal scanner. You will need maybe 4 or 5 shell, but with high gradient and different diffusion time, ideally. The last figure here, which seems to be even more correlated to what we observe in the anatomy, was done with the connectome scanner and multiple diffusion time. If you don't have that, we are less sensitive to the size of the diameter. So you cannot really do this kind of technique with clinical scanner as of today. So yeah, it's not clear also how much of the data. This is an open question actually. How many points do you need on each shell? Do you need shell? Do you need different, just a few points very far away in the Q space, or many? Essentially, you need to be sensitive to the diffusivity of the CSF to kind of model this as the ball. You need to have high gradient to see the differences between the size of the cylinders of the axon. You need, I don't know how many points you need actually. It's something that we need to look at. Depending on the model, this will also vary. So, but the more you have points and the more you have diffusion time and short diffusion time, you can be sensitive to higher or lower diameters. So we are about 2, maybe 1.5 with this data set, 1.5 micron in size in terms of axon, which is a very small portion of the axon in the brain. So there's still work to be done there to be sensitive to more axons, smaller axon.
Okay, so we are going to stop here in the question section. I'm going to the next talk. Thank you very much again, Gabriel. Thank you very much. So I'm sure you're not